Now we've arrived at our last kind of confidence interval that we are going to discuss in this course. And to motivate this discussion, we should start by reflecting about mean and proportion confidence intervals. Namely, the way that we previously thought about confidence intervals is we have some point estimate in the middle and a margin of error that's the same size on either side. So this distance that we call E is the margin of error of our estimate. And so in this way, we get the full interval that estimates our population parameter, which might land here, perhaps, for the sake of illustration. However, with variance and standard deviation, as a consequence of the estimator that we use for standard deviation. So just to refresh your memory, remember that if we're estimating the population parameter, which is population standard deviation, which we denote sigma, we are estimating it using the sample standard deviation, which is the square root of the sum of the squared deviations divided by the sample size minus 1, all square rooted, right? So this is our point estimate. It is the sample standard deviation, and we said that the sampling distribution of n minus 1 s squared over sigma squared is what we call the chi-square distributions, with the degrees of freedom n equals 1. Sorry, n minus 1. We are putting that all together now to construct a confidence interval for population variance and standard deviation at once, where we have to be okay with the fact that we're not going to get a margin of error directly. In fact, what we're just going to compute is a left endpoint and a right endpoint for our confidence intervals, and they're not going to be the same distance from the point estimate. In other words, we're going to get a non-symmetric confidence interval. Okay, and so specifically what we're talking about here, our objective is to estimate, we'll start with the variance. We're going to estimate the variance where we have the conditions that we have a random sample of size n and it's greater than 30, and the underlying distribution is normal. So each data's value is taken independently from the same normal distribution. These are important conditions. These are strict conditions for our confidence interval technique here that we cannot skip. So if these conditions are not met, then we would have to do something else, which is a discussion for a later section. So given a confidence interval, a confidence level, 1 minus alpha, the confidence interval itself is, on the left, we have n minus 1 times our sample variance divided by a critical value So right tail critical value for the chi-square distributions for the left endpoint. I know, counterintuitive, but it's a matter of, because we're dividing, we divide by something larger, that means we get something smaller in the end. And our right endpoint is n minus 1 times the sample variance divided by the left tail critical value. So the way that we want to imagine this is these critical values are taken from the chi-square distribution, which, if you remember, is skewed right and has a support that starts at 0. So you can't get a value less than 0 for critical values. And if we're supposing that we have a left tail and a right tail of alpha over 2 area, then this is our left chi-square critical value, and this is our right chi-square critical value. So for the sake of illustration, we might say if alpha is 10%, right, or 0.10, then this would be our 0.05, 0.05, and these critical values then determine, so this is the value for which the probability that the chi-square distribution takes on a lower value is our 0.05, or specifically more generally, alpha over 2. And because these are both positive values and are not symmetric, we do absolutely need to use a table or technology to find these critical values. And then this gives us our confidence interval once we've constructed the endpoints. Similarly, if we want to find a confidence interval for the standard deviation, all we have to do is take the square root of the endpoints, which is very convenient. This reflects the fact that the standard deviation can be obtained from the variance by taking square roots, and taking square roots preserves ordering. So if the left endpoint is less than sigma squared, then the square root of the left endpoint is less than sigma. So here is our standard deviation confidence interval. And of course, this also means that if we can find one confidence interval estimate, then we can find the other confidence interval estimate pretty much for free. And importantly, these values are determined directly, analytically, and unfortunately the TI-84 does not have a tool for us to do this without resorting to the handwritten technique.